Welcome to The Explainer. All right, today we are taking on the biggest story of all, the entire 13.8 billion year history of our universe. We're going to see how everything went from a single, impossibly dense point to the incredible star-filled cosmos that we see today. Now, how do you even begin to wrap your head around a timeline that long? I mean, years, centuries, they just don't cut it. We need a bigger concept, something we actually borrow from human history, the epoch. Just think of it as a way to split up time into major chapters, where each one is defined by some kind of fundamental, game-changing shift. So for us, an epoch like the Iron Age is all about a new technology that changed everything. But in cosmic history, an epoch is defined by the fundamental physics of the universe itself. Take the photon epoch. That wasn't about tools. It was a time when the entire cosmos was dominated by light. The difference in scale is just, well, it's staggering. So here's our game plan for this cosmic journey. We're going to start in that chaotic first second, watch the universe cool down from a thick fog into a clear space, see the very first stars switch on, and finally, explore this strange, accelerating universe we live in and ask, how does it all end? Okay, we're diving in at the absolute beginning. We're talking about a tiny fraction of a second after the Big Bang. And it's kind of wild to think about, but more happened in this instant than in all the billions of years that followed. This is it, the earliest moment we can even speculate about. At 10 to the minus 43 seconds, that's the Planck epoch. The universe was so ridiculously hot and dense that our laws of physics, everything we know, it just breaks down. It's the ultimate wall, a point in time we just can't see past, yet. Immediately after that, the universe went through this just insane growth spurt. It's called inflation. It expanded by a factor of at least 10 to the 26th in a blink of an eye. And this moment is absolutely critical because it's what smoothed everything out, creating the large-scale uniform universe we see today. By the time we get to 10 to the minus 5 seconds, the universe is cooled off just enough to become this searingly hot soup of fundamental particles. Quarks, gluons, you name it. It's still way, way too energetic for these quarks to actually stick together and form the protons and neutrons that make up our world. This timeline really puts it all into perspective, doesn't it? In less than a millionth of a second, the fundamental forces of nature get locked in, and the conditions are set for the very first stable matter to appear. The entire blueprint for our cosmos was basically drafted in an instant. So after that initial frenzy, things start to, well, chill out a bit. The universe enters this long period of cooling, and this cooldown phase is crucial because it allows the first major construction projects of the cosmos to finally get underway. You know, for a pretty short window, from about 2 to 20 minutes after the Big Bang, the entire universe basically acted like the core of a star. Protons and neutrons fused together, cooking up the elemental recipe for the whole cosmos. About 75% hydrogen, 25% helium. That became the raw material for every single star and galaxy that would ever exist. But even with these new atomic nuclei, you still couldn't see anything. For 370,000 years, the universe was an impenetrable, glowing fog. It was so hot that electrons were just zipping around freely, creating this chaotic plasma. A photon of light couldn't get anywhere. It would just slam into an electron and scatter. It was a glowing, disconnected sea. But as the universe kept expanding and cooling, it finally hit this magic temperature. Around 370,000 years after the beginning, it was cool enough for those atomic nuclei to grab onto the free-roaming electrons, forming the first stable neutral atoms. This moment is called recombination. So what happens when all those loose electrons get locked into atoms? Well, the cosmic fog finally clears. Just like that. The photons, which were once trapped, were suddenly set free. They can now travel across the entire cosmos without bumping into anything. The universe became transparent. And here's the best part. This isn't just a theory. That first burst of light is still traveling through space. Over 13.8 billion years, as the universe has stretched, those light waves have stretched with it, right into the microwave part of the spectrum. We can detect it today. It's the cosmic microwave background, the literal afterglow of creation. So after the fog cleared, the universe entered this strange new phase. It was transparent, yeah, but there was nothing generating any new light. No stars, no galaxies. The cosmos fell into a period of immense, silent darkness that we call the cosmic dark ages. So, how did the universe switch the lights back on? Well, for hundreds of millions of years, gravity just patiently did its work, pulling these enormous clouds of hydrogen and helium into denser and denser clumps. Eventually, the cores of these clumps got so hot and so dense that nuclear fusion ignited, and the first stars blazed to life. Their intense radiation just ripped through the cosmos, ending the dark ages for good. Okay, we're taking a huge leap forward in time now. We're skipping past billions of years of star and galaxy formation. And by about 5 billion years ago, the universe was looking pretty familiar. But then astronomers discovered something that nobody expected. The expansion of the universe wasn't slowing down under gravity's pull, it was actually speeding up. And this chart here, this is the culprit. It turns out that everything we think of as normal, stars, planets, you and me, that only makes up about 5% of the cosmos. 27% is dark matter, that invisible scaffolding holding galaxies together. But the vast majority, more than 2/3, is dark energy. And this stuff is a mysterious, repulsive force that's pushing everything apart, faster and faster. The discovery of this accelerating expansion forces us to ask the ultimate question. If this is what the universe is doing now, where is it all headed? What is the final chapter in this incredible cosmic story? Well, scientists have a few leading theories, and they range from the kind of somber to the downright terrifying. The current frontrunner is the heat death, an endless expansion into a cold, dark, and empty void. But you also have possibilities like the Big Rip, where the expansion gets so violent it tears apart the fabric of reality itself. The crucial takeaway is this: the ultimate fate of our universe depends entirely on what dark energy actually is. So, from a single point to an accelerating cosmos filled with galaxies, we've traced the grandest story we know. And it turns out we find ourselves in this brief, brilliant window of time, the Stellar-Ferris era, the age of stars. It's this thin slice of cosmic history, where light and warmth and complexity are possible, a fleeting moment after the long dark and before the final cold. It really leaves you wondering about our own small but truly spectacular place in all of this.